For any rotating machine, we have to consider these parameters: starting the machine, changing the direction of rotation, either in clockwise direction or counterclockwise direction. This can be obtained either by changing the phase sequence or interchanging the winding connections. Next, controlling the speed of the machine. And finally, stopping the machine, which is equal to braking. These are the controls we have to remember at the time of dealing with rotating machines. The second motor, in case of single phase induction motor, that is capacitor start induction motor. All the connections are similar to split phase induction motor. Only difference is one capacitor is added in the auxiliary circuit. This is starting capacitor. All the operation is similar to split phase induction motor. So this capacitor comes in the circuit at the time of starting only. So earlier, the auxiliary current IA was almost in phase with the supply voltage V, because this is highly resistive. Now, because of addition of capacitance, this auxiliary current leads the supply voltage by some angle. This is because of the presence of capacitance. So here we are concluding the operation. So during starting, both the windings, main winding, auxiliary winding, and one capacitor is also present. When the speed reaches 80% of speed, switch is open. So during running condition, only one winding, that is main winding, is present in the circuit. Coming to the features of the starting capacitance. The starting capacitance is having larger value, so the cost is also high. Electrolytic capacitor is mainly used. This appears for only very short period. That means when 80% of speed reaches, this total circuit will be disconnected from the main supply. So there are two coils. One is main winding, second one is auxiliary winding. R plus Jx, which is impedance of each coil, can be calculated separately. So from these features, we can draw the vector diagram. We are taking supply voltage as reference. As the main winding is highly inductive, this is almost lags the supply voltage by 90 degree. As there is capacitance in the auxiliary circuit, the auxiliary current IA leads the supply voltage by some angle. So the angle between IA and IM is alpha. So the resultant current I is, which is vector sum of IA and IM. And finally, phi is the angle between supply voltage and current. This angle phi is able to develop the starting torque. This makes the single phase induction motor self-starting. So here phi angle is low, so power factor will be high. Power factor cos phi will be high, angle is low. How can we change the rotation in reverse direction? This is simply reverse the terminal connections of either main winding or auxiliary winding, but not both. So this is equivalent circuit, this is vector diagram, and finally speed torque curves. This is torque versus speed. So this is the starting torque with only main winding. If there is no auxiliary winding, this will be the starting torque. This will be the curve if there is no auxiliary winding. And this will be the speed torque curves if there is auxiliary winding in the circuit. So this brings the starting torque, which is near to 200%. So this is the curve when only main winding is present, and this is the curve when auxiliary winding plus main winding both are present. Finally, the torque in the motor is directly proportional to main winding current, auxiliary winding current, sine of alpha. Alpha is the angle between auxiliary current and main winding current. So as sine alpha increases, the torque will be increases. Alpha, it has to be nearly 80 degrees. So as the alpha increases, starting torque will be increases.